Right, so here we want to look at terminal velocity. All right. Now, terminal velocity, let's consider an object that is dropped from rest. Okay, so we assume it's an airplane and a skydiver jumps out. Now, for the purposes of this discussion, we're going to ignore any sideways velocity. So we're going to ignore the fact that he's moving sideways. We're just going to consider downward motion, right? And we are going to think about air friction, but we're not going to consider sideways motion. Right, so initially, as the guy lets go of the plane, or as he jumps out of the plane, before he's actually started moving down, if we just look at the forces on him, the only force on him would be the force of gravity, because he will be subject to the force of gravity. We're going to ignore, he hasn't started moving down yet. This is the instant that he jumps out of the plane before he actually starts moving down. Only force on him is gravity, and so therefore he would accelerate down with a acceleration equal to g, 9.8 meters per second, because the only force on him would be the force of gravity, and we're calling that the net force, right? So the net force is the blue arrow and the red arrow is the force of gravity, and those two are equal because there's no other forces on him. Only got one force, then that must therefore be the net force. So he's about to start falling, but he hasn't actually fallen yet, so his downwards velocity is 0. Okay, downwards velocity is 0. Now, his acceleration, we've said, will be 9.8 meters per second, because that's the only force on him is the force of gravity, and with his mass, we know that we've worked out before that would be his acceleration. Right, but he won't stay like that for very long. There's no friction on him, downwards friction, because he's not moving down yet. His velocity is 0. Okay, so let's consider a few moments later when he's actually fallen a little distance. If he's fallen a little distance, he's actually moving, then he would be colliding with air particles as he goes down. They would be exerting a force on him upwards, and so now he would have a little force of friction pushing him upwards. He's still got the force of gravity on him, which hasn't changed in size. The force of gravity is the same size as it was, but now there's this little extra force on him upwards because he's crashing into air particles. That reduces the size of his net force, because his net force would be this one minus that one. So the net force on him is now a little bit smaller. His velocity is greater than 0. Because his velocity is greater than 0, he's hitting air particles on the way down. That's causing friction. Frictional force is much less than the gravitational force on him because he only just started moving, so the frictional force is still quite small, but it is bigger than 0. It's no longer 0. The frictional force is bigger than 0, but it's less than the force of gravity. His F net is now going to be less than it was. Here his F net was equal to friction. Now his net force, the blue arrow, is going to be less than it was over here, because it's going to be this red one minus the green one. It's the force of gravity on him minus the force of friction, which means his net force is now less than the force of gravity. Because his net force has dropped, we know this equation for acceleration is F net over m, which is this formula just worked around a little bit. And so because his F net has dropped a little bit, his acceleration will have dropped. His mass has stayed constant. And so his acceleration is now less than 9.8 meters per second squared. His acceleration has decreased because the net force on him has decreased, right? The formula that we've been working here, is, of course, F net equal to ma, and a is just the force of gravity in this case. Okay, so let's move on. Now, what happens when he's fallen a bit further? He's fallen a lot further. As he's falling, he is accelerating. Although his acceleration is lower than 9.8 meters per second, it's still bigger than 0. So he's accelerating, so he's moving faster. So every second he hits more air particles. Now let's say his force of friction, it will increase. As he goes faster, the force of friction will increase. Well, let's say now it's increased to the point where the force of friction is the same size as the gravitational force on him. What happens now? Well, if friction equals the force of gravity, then the net force, which would be this one minus that one, is going to be 0. His net force is now 0 because the two forces on him equal each other and they're in opposite directions, so they are balanced and they cancel out. If his net force is 0, if F net is 0, then his acceleration must be 0. Acceleration is F net over m. M hasn't changed, but F net is 0, so A must be 0. So his acceleration is now 0, and his velocity is now constant. He will no longer be accelerating. He will now be moving with a constant velocity, which we call the terminal velocity. Terminal velocity is the final velocity that he'll get to. He will now continue falling with this final velocity, which might be very big. It might be 120 kilometers an hour, but he won't be going any faster. Every second he will just be moving the same speed as he was the second before. So here he had maximum acceleration, here his acceleration is decreased, and here his acceleration is 0. That's terminal velocity. So a whole bunch of points. Initially, the object accelerates at 9.8 meters per second. That means his velocity is increasing every second, but that means he collides with more air particles every second, which increases his the force of friction on him. As the force of friction increases and the upward force of all the collisions increases, it eventually gets to the point where it's equal to the force of gravity. Then he's got no longer any resultant force, therefore no acceleration, and therefore he'll move with constant velocity.